Hello everyone, welcome to my lecture for IB Mathematics Fundamentals, final review before exams. Well, as the name itself suggests, it's a fundamentals course for the IB Mathematics for all students following either standard level, high level, applications or interpretation, or analysis and approaches. It's a final review before exams because I would like to concise every single fundamental thing and the important thing in IB Mathematics to 1 hour or maximum of, let's say, 1 hour or 2 hours, 1 hour and a half video where you can watch the video, have a final review before the exam in the last week or in the last month, and go over them one more time, and then, well, be ready for the exam. So in fact, this video does require a prior learning or the prior understanding of the topics. Therefore, in this lecture, we will just go over the fundamental things, the things that we actually need, and you will see in the exam with high probability, so 90-95% chance that you will have a question about these things almost for sure. Okay, so as you know, IB Mathematics is in 5 chapters. The first one is the number and algebra, then we have functions, and then we have geometry and trigonometry, and then we have statistics and probability, and finally we have calculus. Okay, we will check all of them, and we will check special parts from each topic, and well, we can start, and let's see what we have for number and algebra. Okay, chapter 1, number and algebra. Let's see what are the main parts that we would like to cover here and know for sure. We have standard form, exponents and logarithms, arithmetic sequences, geometric sequences, compound interest, and complex numbers, all forms. Well, the complex numbers, maybe even a few other parts of these subparts, let's say, are especially for high-level students, but overall, again, this thing is for fundamentals of mathematics, so it's for everyone basically. Standard level students who know that they don't have to know, for example, complex numbers, they don't have to watch that part of the video if they would like, but for high-level students, it's necessary to know these things. Okay, so I will leave it to you to pick the parts as you wish. Okay, so let's start. Let's start with the standard form. But before we do, I copy pasted every single formula from the formula booklet that we need in this lecture, in this part, in this chapter. So we have exponents and logarithms, laws of logarithms, formulas for the sequences, arithmetic and geometric. We have complex numbers, compound interest, and that's pretty much it. So first of all, I want to start with the standard form. So the standard form is written in the following way. We have a times 10 to the power k, okay, where a is between 1 and 10. Okay? And the k is element of z, which means integers. Well, how we can use this scientific form as an example, let's choose 728. Okay, how do you convert this from this form to scientific form? Well, we need for sure some a, which is between 1 and 10. Pay attention that the 1 is included and 10 is not included. But 728 is not between 1 and 10. So what we can do? Well, we can move the point from here to here. 72.8 still doesn't help. Then we move one more, so we have 7.28. That works because that number is between 1 and 10, so everything is perfect. So let's use it. So we choose 7.28 as a, so we write times 10 to the power of k. But what should be that k? Well, since we move the point from here to the left 2 times, which means we decrease the number, then in this one we have to increase the number so that the values match. Okay. Well, since we move the point 2 times to the left, we have to increase in this form basically, so the 10 to the power will be 2. So it should be 7.28 times 10 to the power 2. This is just one example for the scientific form, but this is one of the things that they might ask you in the standard level exams usually, but not high level. I haven't seen actually, at least so far. But I think in standard level exams, you do have questions related to this. But this is just a quick example for the standard form and a quick explanation. Let's move on. So what else we have? We have exponents and logarithms. There are certain things that I would like to go over in the exponents. So a few rules that we need. So first rule is that anything to the power of 0 is equal to 1, except when a equals to 0. Okay, we cannot take a to be 0 because 0 to the power of 0 is not defined. Then we have, let's see, a to the power of n times a to the power of m. This means if you have the same base, and if you multiply the same base numbers with different powers, then you can add the powers. So you have a to the power of n plus m. Similar things works with the division. Let's say that we have a to the power of n divided by a to the power of m. Well, this means, again, when you have the same base, a and a, but different powers, n and n, in a division, then you can write it as a to the power of n minus n. One more thing, when you have a to the power of minus 1, that means 1 divided by a to the power of 1, or just a itself. Let's say 1 to the power of 1 divided by a. Another thing is a fractional power of a. So a to the power of n divided by m. Okay, and this would be equal to mth root of a to the power of n. Basically, the numerator will be the power of your a, and the denominator will be the degree of your root. Okay. To give one example for this one, in a certain case, this is not only for the whole numbers, it also holds for the fractional numbers as well. For example, if we have 7 divided by 8 to the power of minus 1, this negative sign means convert the numerator and the denominator to each other's place. So basically you will have 8 divided by 7, but you keep the power with the opposite sign. So it was minus 1, so it will be plus 1. So if this power is, let's say, minus 7, okay, or minus 10, let's say, then this power will be plus 10. Okay. Another example for this, because this is a very common thing that happens everywhere in IB exams. If you have, let's say, 2 divided by 5 to the power of minus k, or minus a, or minus 5, minus 10, doesn't matter, you can still bring that denominator to the numerator next to the 2 as a multiplication. So 2 times 5 to the power of, instead of minus k now, you write plus k. So basically, you can move the things from numerator to denominator, from denominator to the numerator as a multiplication or division, as long as when you do it, you change the sign of the power. Okay. So if, for example, if you had something like this, 2 times 7 to the power of 2, let's say, you can write this like this: 2 divided by 7 to the power of minus 2. It's possible. It's one of the things that you can easily do, and well, there is no problem with this at all. But of course, when we have something like this, we never turn it back to this. But this is just an example for you to understand that you can actually move things from numerator to denominator and from denominator to numerator, as long as you make sure that you change the sign of the power, and as long as you pay attention to the multiplication and division. Okay. So this would more or less cover everything that I would like to say about the exponents. If I remember something along the lecture, I will try to mention it, or in the next part. But so far, I think we have covered mostly everything. There's one more thing, maybe I can show that. When you have a divided by b to the power of n, okay, or some other letter, you can write this as a to the power of n divided by b to the power of n. These things, exponents, are quite important part of the whole IB mathematics, in my opinion, because you have to know these things in order to be able to do the calculations during the solutions of other problems. Maybe the question itself is not about the exponents, but the solution to that specific question, which is about, let's say, calculus or trigonometry, will require you to deal with the exponents, for example. That's why I call this lecture as the fundamentals of mathematics for IB. Okay, let's be done with it. Now we will check the logarithms, and for the logarithms we have the rule. So I will not write much for the logarithms, except highlight the fact that these rules are also quite important, especially this one. So I do see this quite a lot. when you have a power inside a logarithm, you can basically bring that power to the front of the logarithm like this. The remaining formulas also are quite common in IB, so you really need to know them and keep them in mind and practice on them. But this one would be maybe the most common one in my opinion. But of course, while you do remember the formulas for the logarithm, do not forget the definition for the logarithm, okay, where you can have this. So a to the power x, let's say, equals to b. Then that means you can write x as, well, you bring the a to the right hand side as a base of a logarithm. Okay, so logarithm at the base of a of b, you write it. Okay, or if you want to go the vice versa, you can take this a to the left hand side as a base of the power. So you would have a to the power of x equals to b. So this is another way to approach it. To be honest, this is also one of the things that students are struggling with. They do remember maybe sometimes the formulas here, but they forget the definition of the logarithm. To keep this in mind, I would suggest you to remember that the exponent, so the power, and the logarithm, which I have just showed, are the inverse functions of each other, in the sense that one of them takes the power, other one finds that power, or similar things. Okay, so these two things are very let's say connected, and they are inverse of each other. Okay, for logarithms, that's pretty much it. What else we have? Let's see. Arithmetic sequences and geometric sequences. I will cover this in one go for both of them. Sequence is basically a list of numbers, right? So let's say that we have A, B, X, Y, Z, doesn't matter, but we have a list, or the ordered, doesn't have to be ordered there, but you know, list of some numbers, and it goes like this, infinity, let's say. If there is a common difference between the consecutive elements, so between A and B, let's say the difference is 2. If the difference between X and B is also 2, if the difference between X and Y is also 2, and so on for all the elements of the sequence, then we call this as arithmetic sequence. Okay. Example would be 1, 4. See, the difference is 3, so I have to have 7 now because the difference is 3. Then another 3 will be 10. Then another 3 will be 13, and so on. Geometric sequence, on the other hand, is the same idea but with the ratio. So if you have, let's say, A, B, X, Y, Z, okay, and so on, then the ratio of the term to the previous term should be common for all the terms. What it means? It means that if I take B divided by A, that should be equal to X divided by B. That should be equal to Y divided by X. That should be equal to Z divided by Y. Again, ratio of the term to the previous term. For example, we have 2, 4, 8, 16, 32, 64. Now, if you check the ratio, 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. 32 divided by 16 is 2. And 64 divided by 32 is 2. So you see there is a common ratio going on. Apart from these definitions, there is literally nothing else that you need to know about the arithmetic and geometric sequences. I know from experience that many standard level students have lots of problem with these two things, but trust me, you don't need to know anything else than this, except the formulas in the booklet, and which are in the booklet basically. So all you have to do is to understand the context of the question during an exam. So as long as you understand the context of the question and convert that to mathematical terms, then you will be perfectly fine. Only thing that may be additional thing that you need to know about these things is how we denote, what are the notation for the sequences. Well, we call the first term as U1, the second term as U2, third term as U3, and so on, and we call the term number n as Un. Pretty easy. We call the sum of the first, let's say, 5 terms as S5. This means U1 plus U2 plus U3 plus U4 plus U5. If I write Sn, that means sum of all the terms from the first term to the term number n, sum of them. Okay, and this is all the notation that you need so far, I think, for the geometric sequences and arithmetic sequences. There's also sigma notation, but yeah, I will not add it here, but it's also quite important part of IB. But I will leave that to you. I haven't seen that quite often, so I'm skipping it, but these things are quite often. And these things, to be honest, are the 3 points in IB exams. If you keep in mind that you don't really need anything else than the definition of the sequences, arithmetic and geometric, okay? So this one would be called, let's say, geometric, okay? And the formula for them, geometric sequences, sorry. What are the formulas? Let's have a look. So we have here nth term of an arithmetic sequence given to you easily, the sum of n terms of an arithmetic sequence, the nth term of a geometric sequence, and finally the sum of n terms of a finite geometric sequence. So you have formulas for every single thing that you actually need. All you have to do is to convert the context of the question to mathematical terms to understand it all, let's say, mathematically, and then just plug in the values. For example, here, u1 means the first term, un means the term number n, d means the common difference, here r means the common ratio, and that's all. And if you are not sure if what you are doing is correct or not, do not be scared, or do not panic. Just plug in everything that you know. Let's see if you can get something out of it. Okay, at least do some computation, let's say, so that you can get partial marks. Apart from this, there's one more formula for the sequences. There's a sum of infinite geometric sequence. It means if you have a geometric sequence, but you want to check the sum of it until infinity, then what you have to do is basically use this formula, okay? And this works only when your r is less than 1, but in absolute value. So absolute value r less than 1 means your r is bigger than -1 and less than 1. Okay, and that's pretty much it for the sequences as well. Let's delete this part and move on to compound interest. For this, there is not much to say. Also, for the complex numbers, I will explain few stuff. But for compound interest, to be honest, you need the GDC. Maybe I will create another lecture for GDC, for the calculator. But if you don't have a calculator, the formula in the booklet is more than sufficient to be able to solve all questions, almost all questions in compound interest. Because when you plug in the things that you want here, so the FV for future value, PV for the present value, R for the rate of interest, N for the number of the years, and the K is the number of compounding periods per year. For example, if they say that it's compounded quarterly, that means there are 4 quarters in a year, so your K is 4, okay? And that would be it. While you do plug, then you have to solve it, right? So one of these things, so you will plug in here, 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 and one of those things you will not be able to plug in because that's what they ask. In those cases, you might need to use logarithms or simpler equations to solve this thing. That's why, again, logarithms and exponents are fundamentals to the whole IB mathematics, because you have to use them all the time to be able to have a solution to other questions from other topics. Okay. For complex numbers, I have written, I have taken the complex numbers definition. So here we call the A as the real part and the B as the imaginary part. And this is the general form of a complex number. I is the imaginary number where we have I squared is equal to -1. This is the important identity about the imaginary number. Square of I is equal to -1. For high-level students, let's go a little bit more deeper in the topic. We have, well, 3 forms of a complex number, 3.5, let's say. The first one is the general form. The second one is called the modulus argument form, or the exponential, or the polar form, and written like this, with the theta and the cosine of theta and the sine of theta. This one here is your modulus, okay? And this one is your angle, basically. As long as you know your modulus and as long as you know your angle, you should be fine. The third form is the exponential form, and as you can see here, you have your modulus, you have your angle here. As long as you know them, you can write this form. There's also, I said 3.5 because of this thing here. This is just abbreviation for this one. So instead of cosine, they wrote C. Instead of sine, they wrote down S. And that's all. That's just abbreviation. That means exactly the same thing as this one. That's why I said 3.5. But how do you find your argument and the angle? Well, to make it concise, this is how you find it. So let's say that you have an Argand diagram, which is like a coordinate geometry, except on your x-axis you have your real parts of the complex numbers, and on your y-axis you have imaginary part of your complex number. Let's say, for example, you have 2 plus, or let's say 3 plus 4i. That means you have a 3 here and the 4 here, and you have your complex number from here to here, this point, which is the intersection of these 2 points, coordinates, let's say. Your angle that you're looking for is this angle. So this is the theta that is in the formula, and the modulus argument is the length, the argument is the, or the modulus, let's say it's called, I'm not quite sure, sometimes I mistake them, is the length of this vector here. In this case, well, this distance is 3, this distance is 4, right? This is 90 degrees. You can find it easily. R square is equal to 3 square plus 4 square, which means it's 25, right? And R is equal to 5. Okay. Well, that's how you find it. And if you want to find the tangent of, let's say, sorry, if you want to find this angle, well, you know the tangent of this angle now is opposite divided by adjacent. Opposite is 4, adjacent is 3. So all you have to do is to write in your calculator arc tangent, or tangent to the power of -1. It's the same thing, of 4 divided by 3. And this will be equal to your angle that you're looking for. So again, 4 divided by 3 will be your tangent, opposite divided by adjacent, and that's pretty much it. Okay, that will bring us to brings us to the end of the first chapter, I think. Let's see if we have missed anything or no. We haven't. And in the next part, we will talk about functions.